So to motivate the work on electrosynthesis of fuels and feedstocks from CO2, I'll start by acknowledging that we currently rely on fossil fuel sources for the majority of our energy, but there's a lot of potential for that to change. Solar energy and wind are abundant. This graphic is showing total proven reserves of energy in the form of coal and oil and natural gas as the smaller cubes. But the big yellow cube is the solar source. And actually, that cube is representing the annual insolation, the annual energy received from solar, whereas the smaller cubes are actually total proven reserves. So solar is abundant. For a while, it was kind of expensive. I mean, of course, the solar energy itself is free, but transforming it into electrical power and the infrastructure costs associated with making solar modules was previously preventing it from reaching grid parity, so from reaching equivalence in the price of that electricity or the cost of that electricity compared to relying on fossil reserves. But the sector has gone through a remarkable learning enterprise. This learning curve, which as you'll see, is logarithmic on both the horizontal and the vertical axis, shows how industry has made these remarkable reductions in the cost of a solar module. And in the last couple of years, in many jurisdictions, starting with the more sunny ones, solar electricity has approached grid parity with fossil approaches to electricity generation. Now, the solar cells, the solar modules and their cost reduction are of course part of bringing more and more energy, renewable energy to grid parity. And that point is illustrated with this graph. If you go from the blue to the green, you're going to the projected fraction of US electricity that will be derived from solar on the vertical axis when you reduce the cost of that electricity from 6 cents to 3 cents. So that's actually a more than doubling in the extent to which you have a market willing to pay for that renewable electricity. If you add storage, if you add low-cost storage, you can further dramatically increase the exploitation of renewable or low-carbon electricity resources. And the reason for that has to do with intermittency. Conceptually, this is illustrated in the middle. This is the diurnal intermittency. Of course, sun comes up and peaks around noon, but demand is not well matched in time of day to supply. So you need to store, but that's actually something that can be addressed pretty well with batteries. But seasonal variations, where, for example, where I am, got quite a bit of solar source in the summer, but we need a lot in the winter. That requires a really grand scale chemical strategy to move that energy around in time on the half-year scale. And if we don't do that, then the willingness of the market to pay for our renewable electrons diminishes. And that problem becomes more acute as we try to displace more and more traditional or legacy sources of energy with intermittent renewable ones. So storage at the small scale, the daily scale, and storage at the grand chemical scale, the sort of half-year scale, are both very important challenges for the community to address. So there are multiple ways to do that, and our group is focused in, and we'll talk about in today's presentation, on an approach where we take carbon dioxide. In the short run, it could be from point sources like, say, a steel plant. In the long run, it could be through direct air capture of CO2 from the atmosphere. At 400 ppm, that CO2 is still relatively rare, and so it's going to take more energy, it's going to be more costly. But either way, there are technologies progressing to bring down the cost of having reasonably concentrated streams of CO2 available. And you'll see we bring in from the side here the renewable energy, such as from wind or solar, or could be from hydro. And at the heart of the system is the electrochemical CO2 reduction system. And I'll say a bit today about some approaches that take us to chemicals and others that take us to fuels. In the case of chemicals, if we then make them into materials, and if those materials are long-lived, then effectively we've sequestered some of this otherwise emitted CO2, we've sequestered it into a long-lived material. In the case of fuels, as long as we then go capture or we use direct air capture, we've potentially closed the loop and moved in the direction of becoming carbon neutral. So the ingredients, just sort of zooming in on this electrolyzer, the ingredients in this process are, of course, the energy, the reducing equivalents, the electrons. There's the water and the CO2. This occurs at a catalyst, and it's obviously a multi-step, multi-electron reaction to go synthesize more higher value, like multi-carbon hydrocarbons, which are the ones that the sector will typically pay up for. And it will pay up to differing degrees. You'll see here in the gray bars, the current market price per ton of different hydrocarbons. And so for example, methane, you'll see has a very low market price per ton. And if I were to express this in terms of market price per energy, per embodied energy, it would also be very low. Ethylene is higher, though it is a very large global market commodity chemical. Propanol higher still, ethanol more similar to ethylene or a bit less. Some chemicals, and this is kind of a hint at perhaps a go-to-market strategy for this technologies, some chemicals that are harder to produce where the energy efficiency or the carbon efficiency of their existing production methods is lower, look like they may present opportunities. So ethylene glycol and similarly ethylene oxide are potentially quite interesting in that way. Now that was the blue bars, the current market price. The gray bars are an estimate based on some very aspirational targets for how good we could get with our CO2 reduction systems of the cost to produce. And so you'll see, for example, that ethylene suggests that when we meet these aspirational targets, we could potentially produce renewable ethylene profitably, although it's suggesting here that the margins, at least in the first instance, might be low. On the other hand, nice big market. Looks like more of an opportunity for margin with propanol, but it is an order of magnitude smaller market today. Ethylene glycol, which is a fairly big market, looks like a pretty interesting one relative to the projected cost once we meet these requirements. But these requirements on the right, in a way, they're sort of what I'll talk about today. We're not there yet. What is the field of material science and electrochemistry and systems engineering? What does it need to do to move in the direction of these targets so that we could address some multi-billion-dollar, multi-tens of billion-dollar per year markets, such as some of the ones here? So what I have here is a bit of an update. So on the left of each little bar region is where we are today. And then on the right is a target for where we would like to become. So Faraday efficiency, this is going to be a very important metric in what I speak about today. Faraday efficiency is the fraction of the electrons from the electrical current driving the reducing power that go towards the production of a single desired product. So with ethylene, for example, the best results that have been published get to about 80%, but we would like to get higher than that, to at least 95%. That will, of course, mean more of our energy is going towards our desired product, and it will also simplify product separation when we're making a single product with greater purity. Now, there's an additional factor in energy efficiency, which is the voltage efficiency, and that is further off from target. You'll see that some of the most promising systems for ethylene have gotten about a 20% energy efficiency, but we'd like them to get to at least 60% for technoeconomic viability. And then intensity and also reliability are topics I'll talk about as well today, also ones requiring further progress. So I'm going to update a little bit on some recent progress, and of course I'll talk about some of the contributions of my own research group in this progress that the field has been making. First, I'll talk a bit about trying to improve this selectivity and activity. Then I'll talk about addressing the problem of carbon utilization, which is to say the extent to which CO2, when coming into the system, gets mostly consumed in a single pass through the system. And then I'll say a little about some additional reactions that we're exploring. So first, I'll just reference some work from a few years ago where we developed a kind of platform technology for CO2 reduction. You'll see here that we moved from what had been kind of a liquid field with a lot of work in H cells. We moved to introducing CO2 in the gas phase from the backside through a gas diffusion electrode to interact with the catalyst shown in orange, but with that catalyst in contact with the electrolyte. So really the work was to define a well-architected three-phase boundary where gas, the CO2, solid, the catalyst, and liquid, the electrolyte, could all meet up and we could have all the ingredients in place. And when we did, we were able to achieve a Faraday efficiency of about 70%. This was done in very alkaline conditions, very high pH. And that was very helpful to getting the high Faraday efficiency. Created some other problems that I'm going to talk about in a few slides, but one approach to getting high Faraday efficiency is to work with high pH. We did also make some efforts to try to increase the intensity or the activity with which those reactions occurred. And on the previous slide, I showed an approach that was based on a highly planar support. And one of the challenges that happens is that the CO2 gas, when it meets the electrolyte, rapidly gets converted to a carbonate. So we actually don't have too much CO2 that's actually available to react throughout a thickness of layer. So we kind of have a 2D system. And last year we came up with an approach where we would add a strategy to try to transport the CO2 with the aid of PFSA or Nafion to try to get a larger contact area between the high availability of the CO2 and the presence of the reducing power in the catalyst sites. So for those of you who know the organic photovoltaics field, this is a little bit like a Balketter junction, kind of a mixture of the catalyst with the CO2 transporting material in order to increase, if you like, the available area where we had all the reagents per geometric area. And this allowed us to increase the intensity of the reaction. So you'll see here that the current densities are reaching the 1 amp per square centimeter range. And they're doing so while making C2 products, so multi-carbon products. And that ends up getting us into the range of current density that is interesting for keeping the capital cost of these electrolyzers around the similar capital cost to PEM electrolyzers for hydrogen production, which is the right kind of range for technoeconomic viability from a capital perspective. Now, I've alluded verbally a couple of times to some of the challenges that come if you achieve your high Faraday efficiency through alkaline conditions. And that is that the CO2 will react with the electrolyte and produce carbonate. And in these alkaline cells, it's sort of a competing source of consuming your CO2, rather than just participating in the desired reduction reaction, it participates in this downhill conversion to carbonate. And so you end up wasting quite a bit of the CO2 that you strove so hard to capture. So sort of a first step in the right direction is to move to more neutral conditions. And this can be done inside a membrane electrode assembly or MEA system with a neutral analyte. So that's interesting, and it does address one of these challenges, but then you have to sort of go back and figure out again, how can you further increase the Faraday efficiency, because it goes down when you move back to neutral or near neutral conditions. So rather than focus on the catalyst alone, so just a kind of metal catalyst, a lot of copper or copper alloys are used, we recently asked, is there a way to kind of poise the CO molecules that are adsorbed on the catalyst surface and that are near each other in order to participate in the coupling, in the CC coupling? Is there a way to arrange them such that they will have a higher chance of interacting to form the C2 product like in ethylene. And we engaged in a study with Theo Agapi and Jonas Peters at Caltech. The first author here, F. Lee, is Fengwan Li, who's now a faculty member at University of Sydney. And we screened a range of molecules based on bipyridines and found that we were able to change the ratio of COs that were bound in two different available motif. A top binding motif was something we were able to control relative to the bridge motif. And you can even look at that ratio in Raman. And we were able to build a kind of experimental volcano plot where using the optimized molecular adsorbate on top of our catalyst, we're able to maximize the Faraday efficiency under neutral conditions. And as a result, we're able to now make a more robust version of this layer through an electrochemical of the layer onto the catalyst, achieved a 72% Faraday efficiency, but now in neutral media, and thus we're able to report 200 hours stability at a good current density as well, and avoided thus the carbonate problem associated with working in the alkaline conditions. Turns out though, there's always another layer to these onions. Turns out that doesn't solve all the world's problems by any means. In neutral MEA conditions, you are still producing hydroxide locally, and you still have the potential for CO2. And in this case, you are particularly concerned about crossover of the carbonate, so the CO3 2- through the AEM to the anodic side, where it will then evolve CO2. It was evolving CO2 on the anodic side at the outlet. And so now you have, if you want to use all your CO2 rather than discard some, you'll need to recycle that. You'll need to reintroduce it on the other side of the system. And so you still have an issue that needs to be addressed here. In the flow cell, shown here in the left column, the CO2 utilization was only 17% because dominant carbonate formation occurred. In the MEA system, CO2 utilization is a little higher, 35%, but now you're crossing over to the anodic side, so you still have a separation problem that you need to address. And that's ultimately going to cost energy, and it's going to cost dollars. So per ton of product, and the product we're making here is maybe worth $800 or $1,000 per ton, you have a $160 penalty approximately in the alkaline system, and still a $100 penalty in the MEA system. So we have recently sought routes to avoid that penalty, and we've taken a few approaches that are pretty interesting. So one of these is to sort of embrace carbonate, if you like. Carbonate, of course, is used as a means of CO2 capture. And 2 years ago, we reported a system that used as the liquid electrolyte CO2 in the form of carbonate, and then added a bipolar membrane to locally produce proton to react to produce CO2 that could then be reduced at the cathode to a mixture of carbon monoxide and hydrogen. So effectively, we were producing CO, we were also producing some hydrogen. So if you look at the sum total of those two products, effectively we're producing syngas, and it was with a full cell efficiency of about 35%. But the advantage here is it avoids the carbonate problem because it directly reduces from carbonate, and it is working with a capture liquid. So it actually sort of took over one of the steps that we normally count on another part of the system to do. So instead of regenerating the carbonate and producing the gas phase CO2, we take over that step as well. So we go from capture liquid to syngas. Amines are another popular approach for capture technology. And we did something similar with amines, where we worked with MEA, and found that we were able to get a Faraday efficiency to carbon monoxide that was about 70% and a higher full cell energy efficiency of 40%. So both of these capture liquids are potentially amenable to this direct use of capture liquid approach. So in terms of other strategies for high CO2 utilization, one is the production of carbon monoxide is reasonably advanced, high TRL. So you can avoid this carbonate problem by taking a tandem approach and coupling an existing solution for CO2 to CO with a best available, or with research on improving CO reduction to ethylene. But I'm going to say something instead a little bit about another approach, which is based on an acidic electrolyte on the cathodic side, and that we reported a few days ago in the journal Science. So the motivation to be interested in the acidic CO2 reduction is that it's kind of obviously, it's the opposite of that alkaline condition. And so it has the potential to avoid the carbonate problem. And so it even is so far from the neutral conditions that you can avoid also the CO2 crossover problem that I talked about in the neutral case. And you are dealing with a very conductive electrolyte, so that makes your life easier compared to neutral conditions. The problem, and it's a fairly big one, is that previously hydrogen evolution has completely dominated. You see here the Faraday efficiency for hydrogen at low pH of 1, 2, and even 4, and you see a dominance of HER. So if you're in the business of trying to reduce CO2, you obviously had a problem in acidic conditions. But what we came to realize recently was that the origins of that problem were related to a sort of inability for the CO2 to be interacting with the catalyst under these conditions. And so we were getting severely outcompeted by the effect of the hydrogen evolution process. But the first author of this work, Eric Huang, realized that if he could add significant KCl, so he could put in a lot of, in this case, potassium cation, that he could start to develop conditions where you see here, as he puts in more and more potassium cation, these non-HER products start to emerge. You can see the emergence of methane and eventually of ethylene. And he optimized this. He worked with one of these high surface area catalysts based not just on the copper, but on the copper and the PFSA. And he was able, under acidic conditions, to get to Faraday efficiencies for C2 plus products of about 40%, with a significant additional component of C1. So CO2 reduction began to dominate. But then the big advantage over prior works was that this cyan curve here on the far right, SPCE, which is the single pass conversion efficiency. So it's the utilization of the CO2 input. It's how much of that CO2 participates in reduction to one of these more valuable C1 or C2 products. That he was able to get as high into the high 70s, where all these previous approaches that I've been describing were stuck in often in the 10s or the 20s or maybe the 30%. So he was able to utilize his CO2 thanks to the avoidance of carbonate and the avoidance of crossover. I'll give a little taste of another direction that we're interested in, and then I'm going to transition over to Brandon for him to talk more about the methodology of materials discovery. And I've been very focused on the cathodic side, right? I've been over here where we've been reducing CO2 to C2H4, for example. And I've just been assuming something on the anodic side. In fact, most of us just assume oxygen evolution, but not as something that will bring market value, but just as something that kind of balances the current across the system. But this group knows very well that selectively oxidizing hydrocarbons towards, for example, alcohols and epoxides is actually a value-adding reaction that needs to be done at scale in the chemicals industry. So if you could get selective, you could actually not just add market value on the reductive side, but also on the oxidative side. So we've recently turned our heads to this. and have looked at going from ethylene to ethylene glycol, but electrochemically in a single step in the electrolyzer on the anodic side, and recently reported a 70% Faraday efficiency for ethylene to ethylene glycol based on a palladium gold dendritic nanotube catalyst. And then last year took a different approach, one that was actually inspired by the chlor-alkali approach, and used a redox mediator strategy to get to a very high current density. We got to about an amp per square centimeter current density and a Faraday efficiency of about 60% for going ethylene to ethylene oxide. And we think, as you can see over here on the right, that given the capital cost reductions that are achieved this way, that it suggests a route that has technoeconomic progress by really making coupled reactions. So that's one of the directions we're headed in generally. You see here on the right, a coupled electrolyzer. It can just make hydrogen. There's still lots of problems to solve on the technoeconomics of hydrogen, right? And even with really good energy efficiency in water splitting electrolyzers, say around 70%, the willingness of the market to pay for hydrogen at $4 or $5 a kilogram is really limited. And so if you can potentially lower the overpotential by doing a selective oxidation on the anodic side, and just also generate a companion product that has market value, then this gets potentially interesting. So for example, propylene to propylene oxide, ethylene to ethylene glycol that I spoke about, xylene to terephthalic acid. These have large carbon footprints. Significant portions of those carbon footprints are attributable to the direct emissions, not just the energy component, but relative to the not perfectly selective oxidation reaction. So there's an opportunity as kind of a future path for this field to try to achieve very selective anodic processes, can add market value, and can do so in a way that allows coupled electrolyzers to bring us closer to technoeconomic viability. So I'm going to let Brandon take over and say a little bit about some of these methodological developments in how to accelerate catalyst discovery. And then Brandon and I will wrap and we'll go to questions. Brandon.
Thanks, Ted. I will go ahead and share my screen. I have the same slide ready to go. Just, yeah, perfect. Okay, so Ted presented a lot of great work and a lot of progress in this technology, but you know, we're impatient people. We want to ask, can we accelerate how we develop this technology? Can we do something different in its overall discovery pipeline to try and bring this to market faster? So, you know, Ted's had a ton of success doing this using what I call like traditional catalyst development. This involves typically slow computational screening, so using first principles calculations to try and understand the structure property relationships of catalysts to try and predict, is this going to be a very good catalyst for this particular reaction that we're working on? And then typically slow fabrication, so, you know, student, postdoctoral fellow fabricating one catalyst, analyzing the results, making electrolyzer devices of promising candidates, and kind of repeating this process. But catalyst design is very complicated. There are so many different things that you can do. You can nanostructure the catalyst, you can change its composition, change its shape, put it on different supports. There's just so many different things to play with. So I'm going to talk a bit about some efforts we're doing to try and change the way that we discover new catalysts using advances in AI. So this comes out, my role in this presentation is that I'm the director of A3MD, which is the Alliance for AI Accelerated Materials Discovery. It's an alliance that Ted has set up, joint with some academic institutes and partners LG and Total. And we're working to use AI to accelerate materials discovery, just generally to try and change the paradigm of how we discover materials. Our main thrust at the moment is focusing on high performance catalysts. So what we're trying to do is replace conventional materials discovery, which looks something like this. You start with the periodic table, which is a lot of combinations of different chemical elements. And you use, you know, past literature, some human intuition, to try and bring that down to some manageable number of compounds that you think might have reasonable properties for some given application you're working on. You can then use slow computational screening, so first principles calculations, to try and bring that down to some manageable number of compounds that you think might have high performance for a given application, say in the hundreds. And then with that, you can synthesize one, you characterize one, make a device if it looks promising, and kind of continue this feedback cycle until eventually you have something that might be compelling enough to bring it to market. So we're trying to replace this with AI accelerated materials discovery. The way we do this is we start by simulating a large number of compounds. This is kind of the rate limiting step. You need a lot of different training data. So we can do this using first principle calculations to simulate as many as we can. We dig around to existing databases to get as much data as we can. Then we use this to train machine learning models, which enable us to very rapidly explore a vast number of compounds. And then we can then screen those for properties of interest, and then bring that down to sort of the thousands of compounds range, which is something that we can then use robots to synthesize in parallel. So instead of one person making one catalyst a day, we can have robots that can synthesize hundreds of catalysts a day, and then robots that can then characterize hundreds a day, make devices out of promising results. And then by doing this, we're, instead of just doing one experiment and analyzing it, if we're doing hundreds at a time, we're generating a lot of data. And with this data is an opportunity to use AI again to learn trends that may not be obvious to humans and to better guide experimental design cycles. So the goal is to try and accelerate every single step of the process, and then to also try and do things smarter to increase the chance that any given experiment will produce desired outcomes. So an example of this, we published this last year, was using active learning to discover carbon dioxide reduction catalysts. So if we want to turn carbon dioxide into multi-carbon products, typically copper has been used, it's been shown, or copper-based catalysts have been shown to have the best performance. So it even studied 244 base copper catalysts. That's about 12,000 surfaces and 230,000 different absorption sites. So that's a lot of computational time to be able to try and go through each of those individually. So what we did was we carried out some DFT, some density functional theory first principle calculations to calculate CO absorption energies on a subset of these sites. Now, the CO absorption energy has been used as a good proxy for catalytic performance. We then use that as training data to train a machine learning model that can predict CO absorption energy on all the 230,000 sites. We look at the ones the best candidates that it predicted, and then we verified that using our first principle calculations, which then fed back into our machine learning model as additional training data. So we have this sort of active learning closed loop cycle to try and optimize, reduce the error of the model, and then get to a model that can predict all of them rapidly. So by doing this, we were able to screen through all of the sites using only 4,000 DFT calculations. We then plotted all the different candidates that we looked at, all the different copper-based compounds. And here we plot out their activity for CO2 reduction and their selectivity. So on these two plots, things that are more red are better performing. And what we found was it was these aluminum copper compounds that typically had the best combination of activity and selectivity. We then looked at all the different compounds and tried to reduce it down into a latent space that kind of finds groupings of different absorption sites. And we were looking for CO absorption energies near about that minus 0.67 range, which was kind of found to be optimal, particularly through activity. And we found is that these copper aluminum catalysts, there was a copper active site that was rich in aluminum in its environment, has sort of the optimal CO absorption energy. We went in the lab then and tried to fabricate these what we call de-alloyed copper aluminum catalysts. And we tested it, integrated into an electrolyzer and tested against relevant controls. And what we achieved was, at the time, was a record Faraday efficiency of over 75% at a high current density for reducing CO2 to ethylene. So this was an example of sort of an AI accelerated discovery of a new catalyst that exhibited very high performance. So what we're kind of doing now, and with our A3 initiative, is not just, that was an example of accelerating, purely the computational portion. We're trying to accelerate all portions, including all of the experimental elements. So we have a robot right now that can synthesize over 150 catalysts a day. We have characterization systems that can now test over 150 per day. And we're working towards these autonomous discovery platforms, really trying to remove as much as possible the human manual effort required and let all the robots, machines do all the work. So trying to get things that automatically can then decide what experiment to run next, automatic error correction, having the entire system integrated. We were joking around the other day about trying to, do we get a robot to help transfer samples between different labs? But anywhere we can make things autonomous would be an acceleration of the system. So the goal is not to just replace humans and make them, useless. It's to get rid of all the manual elements, and then what it'll do is reward scientists for spending more time on trying to ask the right questions and develop systems and processes to get those answers. So that's kind of the thing that we're working towards now, towards accelerating how we can develop these catalysts and how we can try and accelerate how we bring this technology to market faster. And then I'm just going to toss it back to Ted, who can just talk about this last slide, talk about the overall roadmap for this technology.
Thanks, Brandon. And really appreciate that discussion of, as you say, accelerating the methodological aspects. So some of the key steps here, I talked about how in the short run, we think that this tandem approach where CO2 to CO, which is high TRL, can then be combined with efficient CO to ethylene. So we're putting a major emphasis on that. Our progress in the acidic CO2R that I talked about is also encouraging. There we need to figure out how to lower the total full cell potential. And then still looking out a few more years, there is more work to do to get all the way to scaled industrial implementations of CO2 to ethylene and CO2 to ethanol and propanol. And one challenge area that's very interesting, that's quite uncracked, as it were, is to go to higher carbons than C3. So certainly increasing the Faraday efficiency to C3, but starting to figure out how to do electrochemical synthesis nearish room temperature of C4 and above is hard and substantially unseen, and so quite an interesting direction for the field. And Brandon and I are all yours for questions and for discussion. We'll take a look on the chat, although I'm guessing people might also want to just ask questions live. But just before we go to that phase, we wanted to note that this was the work of a large and very talented and very diverse group of grad students and postdoctoral fellows. And we also wanted to just draw your attention to places in case you wanted to read more. The papers are available to you at light.utoronto.ca. And we're very happy to follow up, of course, with emails to give you more information and more papers, but we did also want you to know about the repository of papers at that website.